All right, let's get right into it. We are going to tackle one of the biggest, most painful bottlenecks holding back large language models today, the key value cache. It's an absolute memory monster, but thankfully, some really brilliant architectural fixes have managed to tame it. And that's exactly what we're going to break down.
And you know what? That is not an exaggeration. As our models get bigger and we demand larger and larger context windows, this problem goes from annoying to absolutely critical. So today, I'm going to show you exactly how two key innovations, grouped query attention and multi-head latent attention, solve this crisis. We're going to see the exact tensor compression that lets these models chew through 1,000,000 tokens without breaking a sweat.
Okay, so first things first, before we can even talk about the solutions, we have to get a really solid handle on the problem itself. Why is the KV cache such a VRAM nightmare to begin with? So think of the KV cache as the model's short-term memory. It's super important. For every single token you feed the model, every word, every piece of a word, it generates and stores a corresponding key and a value tensor. This cache is what allows the model to look back and remember the context of the conversation when it's deciding what to say next. Now, the real source of all our pain lies in the standard architecture, what we call multi-head attention, or MHA. In MHA, the model uses these things called query heads to ask questions about the context. And here's the problem. For every single one of those query heads, the model has to create and store one key and one value head. It's a very rigid one-to-one relationship, and it has a pretty disastrous consequence. And this is that consequence. As your input sequence gets longer, the KV cache just grows and grows and grows linearly. 100 tokens, 10,000, 100,000, it doesn't matter. The cache just keeps expanding, token by token, until it has eaten up every last bit of your GPU's VRAM. And at that point, boom, it's over. The whole thing just crashes.
Right. This is the billion-dollar question in AI right now, isn't it? How do we get the incredible power of these massive context windows without paying this brutal memory price? Well, that leads us right into our first major innovation.
So the first big fix is something called grouped query attention, or GQA for short. And it is just an incredibly clever, really elegant change to the model's fundamental architecture.
The big idea is right here. Instead of that strict one-to-one pairing for multi-head attention, GQA basically asks, hey, what if we just didn't do that? What if we made a group of query heads, say 8 of them, all share a single key and value head? And you can see exactly how it works here. All those separate query paths now converge on one shared destination for their key and value information. It's a pretty simple structural tweak, right? But by breaking that one-to-one rule, you completely rewrite the memory equation, and the result is a huge, huge reduction in the size of that KV cache.
How huge? Well, in a typical setup where you group 8 query heads together, you get an 8-fold reduction in your KV cache memory usage. Just like that. An 8x saving on memory is an absolute game changer when it comes to actually deploying these things in the real world. And here's the best part, the real kicker. You'd think a change like this, saving so much memory, would have to hurt the model's performance, but all the research shows it has a practically negligible impact on accuracy. It is one of those incredibly rare engineering trade-offs where you get this massive win with almost no downside. But what if we want to push it even further? Well, that brings us to the really bleeding edge stuff. You see, if GQA is an elegant architectural surgery, then multi-head latent attention, or MLA, is just an act of pure, brute force mathematical compression.
Yeah, the whole philosophy here is completely different. Instead of trying to be clever and store less stuff from the get-go, MLA's approach is to just ask, what if we just take the entire massive KV cache and use math to violently crush it into something tiny?
And the technique it uses is called latent vector projection. You take that absolutely giant, high-dimensional tensor that is the full KV cache, and you multiply it by a specially trained matrix. What comes out the other side is a tiny, super dense, low-rank vector. It's a compressed mathematical shadow of the entire cache. This is it. This is the operation right here. This single matrix multiplication is what achieves that violent compression. The entire enormous KV tensor gets multiplied by the projection matrix, and what you get is that little latent vector. That's the heart of MAL. Now this is where the real magic happens, especially at inference time. The model never actually stores the full uncompressed KV cache in VRAM. It only holds on to that tiny latent vector.
Then, for the tiny fraction of a second it needs to do the attention calculation, it multiplies by another matrix to decompress it on the fly, uses it, and then, poof, it throws it away immediately. It's an absolutely incredible memory-saving trick. So we've looked at an elegant structural fix and a brute force mathematical one. But what does all of this incredible engineering actually unlock for us? What does it mean in the real world? This table really lays out the trade-offs perfectly. Your standard MHA gives you no memory savings. That's our baseline. GQA gives you high, like 8x savings, with a negligible performance hit, and it's moderately complex to implement. Then you have MLA, which offers extreme savings. We're talking more than 10x, with only a low impact on performance, but it's significantly harder to get right. But at the end of the day, here's the punchline. Techniques like GQA and MLA aren't just cool ideas in a research paper. They are the fundamental breakthroughs, the key technologies that are allowing the latest generation of models to process context windows of over 1 million tokens. They are the direct solution to that VRAM starvation problem we started with.
So, we broke the memory wall with the KV cache. That's a huge step, but it really makes you wonder, right? What's the next big bottleneck we're all going to have to face in AI? Well, if you want to find out how Mixture of Experts is tackling the next big problem, the feed-forward bottleneck, you can check out our explainer on that right here. Thanks for watching.